Okay, let's get started here today. First of all, I want to welcome everyone to something the Coalition for Deep Space Exploration has done for the first time. My name is Frank Slazer. I'm the president and CEO of the Coalition for Deep Space Exploration. It's a space industry trade association representing firms from around the country and focused on space industry issues, deep space exploration, space science, and space technology development. I want to welcome you to the first session of what we and our members hope will be a series called Space 101. Actually, there's a series called Space 101. It's a virtual education series for reporters and space social media publishers in advance of NASA's Artemis 1 launch. Artemis 1 is the start of our nation's return to the moon, and it likely is going to get the attention of people around the nation and, in fact, around the world. While you're going to be doing the reporting and the analysis, we want to make sure that we can help you by providing the technical background behind what you're going to be seeing, because we're convinced that assuring it's understood by you and as a consequence by the American people is incredibly important. Speakers for today's session, and maybe you could just raise your hands as I call your name out, are going to include Dr. John Blevins, the SLS Chief Engineer for NASA, Doug Bradley, who's the Deputy RS-25 Rocket Engine Program Manager at Aerojet Rocketdyne, and Mark Tobias, the Deputy Chief Engineer for the SLS program at Northrop Grumman. Topics covered by them will be a wide range, including the rocket equation, why NASA chose an expendable rocket design for this mission, why the combination of the RS-25 engines and solid rocket boosters were chosen for the SLS. And you're also going to be able to ask questions in the chat, which will be moderated by Mary Angola, who's the Senior Manager of Space Communications for Aerojet Rocketdyne. They're going to be answered at the end of the overview discussion. And then, John, I think I'll just turn it over to you.
All right. Thank you, Frank. So super excited to have all of you and very excited to be the first session of our Space 101 series on rockets. So thank you, John and Mark and Doug, for helping me kick this session off. So all of them are great resources, very technical guys. So before we get started with all of our questions, we thought it'd be good just to go over some basic definitions. So first one is ISP, and so Doug, I'm hoping you can tell everybody what ISP is and why it's important and how it relates to rockets.
Yeah, I will. Hi, everybody. ISP, we call that gas mileage for a rocket engine. You can imagine that would be really important. ISP stands for specific impulse, ISP, and it is basically how much thrust you're generating per pound of propellant you're using up per second. So it's thrust for how much propellant you're using. That's why we call it gas mileage. You can imagine the higher the ISP, the more thrust you're getting for less propellant. Every pound of propellant you don't have to fly is a pound of cargo you can fly. So really a critical and very important part of rocket engine building.
Thanks, Doug. All right, Mark, tell us about Delta V. Looks like we got a little time lag with Mark. Okay.
Yeah, it seems a little laggy. Why don't you skip me? I'll call in, go through the phone.
All right, sounds good. All right, John, do you want to tell us about Delta V and Max-Q?
Yeah, I will. As Mark was about to say, Delta V is a little bit of what it sounds like. It's a change in velocity. What's really important about Delta V is just to remember that change in velocity takes a lot of energy. When we say Delta V, we're talking about energy when it comes down to it, right? So, hey, let me tell you about Max-Q. I think that's what Mary's going to call on me for. Is that right, Mary?
That'd be great.
Hey, so in engineering, we use this term Q to represent dynamic pressure, right? So that's just in the equation, we'll say Q equals, and then we've got the equation for dynamic pressure. And so we have a maximum dynamic pressure that we associate with a period of flight. You see a chart over here to the left. It may not mean as much to you as, say, an altitude chart, but as we go through the atmosphere, we accelerate. And of course, we accelerate all the way to orbit on a rocket. And we get to a point where we're at a combination of the maximum density and acceleration we're going to get in the low atmosphere. And when that happens, we pay particular attention to the loads. There's a couple of things going on, very close timing. We go through what we call transonic, and then we hit a Max-Q. And that's where those forces give us the maximum bending moments. You can imagine a pencil flying through the air and it wanting to bend. And so we pay particular attention to the protuberances, things that are attached to the rocket itself as we go through max Q. And you're probably familiar that the shuttle would even throttle down during that period in order to survive the loads a little bit better. So it's a really important part for us, and we a lot of times just call it max Q. And so you think maximum dynamic pressure when you hear that.
All right. So, Mark, are you back with us? I was not able to hear Mark. Were you all able to hear Mark? No. All right. Well, we're going to work on Mark's audio, but we'll keep going.
Mark,
So,
it looks like you
this is
have
Rocket
yourself.
101. What is the definition of a rocket? And John, I'm going to go to you for that.
Yeah, I'm going to give a simple definition here. You know, we could go back to where the Chinese flew little rockets that are like fireworks. But in reality, when we say a rocket, we're usually talking about something that we mean kind of like a launch vehicle. And that's what you guys mean. One distinction that I want you to know to carry away with you on rocket is usually when we say rocket, we mean that you're carrying the fuel and the oxidizer, everything needed for that component in one piece, right? A jet engine breathes air from the atmosphere, but a rocket, we combine that fuel and oxidizer, and it's to do a lot of different missions. In our case, it's going all the way to the moon and beyond. But in a lot of cases, it can be, as you've just seen recently, with flights that are suborbital, just like Alan Shepard's flight was originally. And so a rocket is just a way to propel us, to expend mass out of the back. That's one thing that is very common with rockets, is we are taking a mass and we're throwing it out of the back end in order to get a force going the other end to propel this vehicle.
All right. So, Doug, you're our rocket engine guy. So we often think of rocket engines on the bottom of launch vehicles, but they can go on spacecraft too, right?
Yeah, absolutely. There'll probably be different types of rocket engines. We've got on the spacecraft, on Orion spacecraft, on the service module that pushes it around in space, we have monopropellants and bipropellants. Bipropellants, you just mix them together and they combust. Monopropellant, you just have one propellant, put it through a catalyst, and it combusts. Those are pressure fed. Those, the tanks that feed that propellant are just pressurized, and they push that propellant through the engine. And so those are for the upper stage engines, Orion and service modules and the like. The larger rockets like the RS-25, they're going to be turbo pump driven. They're going to be pump driven engines. You can't pressurize a large tank like that. It would just be too heavy. So you have to take that propellant, pump up the pressure with pumps and drive it through the engine. We'll be talking about that more, but is that enough for now, Mary?
Yeah, I think that's good. So when we think of rockets and rocket engines, there's a lot of different propellant combinations. So there's chemical, there's nuclear, there's solar. And so I want to go through some of those different propellant combinations and sort of what the advantages are. I'm going to go to John first because I'm a little bit scared about Mark's audio, so hopefully we're getting that worked out. But John, do you want to talk a little bit about nuclear propulsion and solar propulsion? I think you're muted.
Yeah, I think you're muted.
Well, that was probably my best words of the day, but let me back up here. I'm glad we're really taking the time to look at everything, even the things that aren't on the first Artemis mission. So let me talk just a little bit about nuclear and even some advanced propulsion concepts that go on. You know, most of the time, you know, just like Doug was talking about in the chemical rockets, whether that's a two component like a bipropellant, or even like on our RS-25s that use hydrogen and oxygen, you're taking that chemical bond energy and you're breaking those bonds, you're turning that to thermal energy. Then that thermal energy is converted to kinetic energy because of the rocket equation wants that velocity out the back end of the rocket. And in the case of nuclear, you're actually getting that energy source instead of from those chemical bonds of different propellants or even the same propellant, you're getting it from nuclear reactions. And so the basic nuclear rocket would be one where you've got a fission reactor, and then you have a way to transfer that heat into a substance. And generally that's going to be a very low molecular weight. And that's because low molecular weight products like hydrogen they produce the maximum velocity out the back end. And so typically a nuclear rocket, like one we've studied in the past, one that we started in the 60s and one we could use for later Mars missions, those would be a hydrogen propelled device that used nuclear energy in order to get started. There's other concepts as well for nuclear propulsion, but they're all expanding some type of material with nuclear source as the heat, as the energy. And let me just mention, Mary, I think I'll just mention one other type of propulsion. We have solar propulsion that also uses solar as the heat. And I'll mention that there's work going on even in solar cells. That's the only one that we're going to talk about today that isn't where you expel something in order to provide thrust. In the case of solar cells, you've got a big surface area and you're using photon pressure in order to transfer energy to try to propel a device. That's a little different, and that's why they call it a cell as opposed to an engine like the other things. But I think that answers your question, Mary, on the basics of nuclear propulsion.
Yeah, so, we're going to talk mainly about chemical rockets today and chemical propulsion systems. And so one of those is the solid rocket motor. So, Mark, we're going to try to see if your audio is back working.
Mark, you'll need to unmute yourself on your computer audio.
Can you hear me now?
Yeah, sounds great.
Yeah. Great.
Okay. So solid propellants are a combination of fuel and oxidizer that are bound together by a polymer. So rather than having separate tanks for fuel and oxidizer, you actually have the fuel and oxidizer already mixed together in the right ratio in a polymer binder. And so once it's ignited, it burns at a predetermined ratio, and like John said, expels hot gases just like any other rocket. The advantage of solid propellants, you can get really, really high volumetric loadings, and so you can get a lot of propellant at high density in a small space, and they're storable. They don't age out, which is why solid propellants have been used for many, many years in strategic missiles, in silos.
Thanks, Mark. Glad we were able to get the sound working. So, Doug, on the chemical propulsions, you talked a little bit about the different types, the monopropellant, bipropellant, et cetera. But can you talk a little bit about the different cycles? So, especially on the large liquid rocket engines, what are the different cycles that you can see in those engines?
Yeah, there are several different engine cycles, we call them. One is a gas generator cycle. The Apollo rockets were that, the F-1 rockets, where you have a gas generator that burns those propellants, as John was describing, but they take that exhaust and put it through a turbine to spin a pump, and that gives the pressure that you need for that rocket engine. Now, most of those gas generators, they are really great for lower atmosphere booster rockets, but they do dump a lot of propellant, so they're not quite as efficient. Then there are expander cycle engines like the RL-10 that we're going to fly in the second stage. They use the latent heat of the engine itself to heat up propellants and drive turbines. They are great and efficient. They typically can't get as high of a thrust as a GG cycle. And then finally, the RS-25 engines are called staged combustion. And that's one of the reasons they're so efficient. As the name would apply, we tend to burn the propellant in stages. We take a lot of propellant, put it in pre-burners, we pre-burn it. We use that exhaust to drive turbines, which drive the pump. Then we actually take that exhaust, we don't dump it overboard, we put it in the main combustion chamber. And there's a picture of it right there. It's kind of a simplified schematic. And so we're taking all of that propellant and eventually putting it into the main combustion chamber and the main injector, kind of right in the middle of that picture. And there's a lot of it. John talked about, expelling as much propellant out of the back end of the rocket at the highest speed possible. And so we're we're consuming propellant at the rate of about a swimming pool every 20 seconds, incredible amount. We're throwing it out the back of the nozzle at about 9,000 miles an hour. And so that's why we can get this 500,000 pounds of thrust. But for this rocket cycle, we're using all the propellant. We're burning almost every molecule of propellant and turning it into thrust. We're not dumping it overboard. And so that's why this particular rocket was really good for this mission, because we call it a stage and a half. It has to work good as a lower atmosphere booster rocket, but it actually has to work also in out of the atmosphere. And so this is a good compromise, and we get good performance all the way uphill.
All right. Love the gas mileage that engine's getting you. So, all right. So let's go to the rocket equation, because, Frank advertised that, and all of his advertisements, you all are going to talk about what the rocket equation is. So why don't we just start with that? That's a great question. So, John, I'm going to go over to you for that one.
The rocket equation is really simple in its form. It's this logarithmic relationship between the initial and the final mass. And really what's important there is for you to understand it's not linear. And that final mass is really small when you cheat gravity. And so that rocket equation really drives this exponential, if you will, relationship. It really drives us to think very hard about mass. And of course, any flying vehicle, whether it's an aircraft or whatever, thinks a lot about mass, but nobody thinks about mass like a high energy rocket does. We go with much lighter mass margins because, and this equation you see over on the right, where you can see has that natural log of the original over the final mass there. And so ultimately that equation, though, drives us toward all the other complications. That simple equation drives us toward wanting to optimize that mass. Let me talk about what's on the outside of that natural log just a little bit. And Doug really hit on it well, and why we use that RS-25. And that's the exhaust velocity of the propellant that we're throwing out to get that change in energy, that delta V. That exhaust velocity is highly optimized with the RS-25. When you don't have a big ratio between those two, you can play some games, and that's why we don't look for high exhaust velocity coming off the ground. That's why boosters a lot of times will be hydrocarbons, or as Mark mentioned, this kind of pre-mixed, very well packaged, very dense, solid propellant that gives us this great thrust. Because we have another limitation. This rocket equation is not our only limitation. When we leave the ground, we have to have a thrust to weight greater than 1, or we don't move. And so we're balancing the rocket equation, which we could optimize with a very high velocity jet, with the requirement that we've got to have more thrust than we do weight at any particular time until we get out into a reasonable velocity very close to orbit. And so anyway, that's kind of some summary, Mary, of what we look at in the rocket equation. It certainly drives everything we consider. It drove the original Apollo team to look at staging because of the issues they would have with mass. And certainly it drives a lot of our decisions when we come and we look at mass and the way we're doing things and the way we put the rocket together with very, very high exhaust velocity on the final stage of the rocket.
And Mark, I know you have a lot of thoughts on sort of the rocket equation, how those translates, but so I'll let you add those if you have anything you want to add. But I do want to ask you, I think this is a good segue for reusable versus expendable rockets and sort of what the difference is. And, a question a lot of folks ask is why SLS was chosen to be an expendable rocket. So I'm hoping you can, that's a lot I just threw at you, Mark. So I'm hoping you can attack it, and then if you want to bring in your friends to help you answer anything, that'd be great.
Yeah, whether you reuse or you expend a rocket is kind of a complex calculus of various different factors. It comes down to how many times are you going to fly the rocket, how expensive is the hardware to build in the first place, how available is the hardware that you are building, how survivable is it in a recovery environment. Some of these things, we splash down in oceans, they re-enter at very, very high velocities. How survivable are they becomes a factor, as well as can you afford the performance penalty of putting recovery systems on your rocket, because that rocket equation says you want that final mass to be light. You put recovery systems on, you're adding mass that's not contributing to velocity. So it's really a business calculus as to whether or not it makes financial sense to recover or expend. SLS chose to expend because of its flight rate. You know, when you're flying once a year, you don't have a huge flight demand for your hardware where you need to turn your hardware around a lot. We had a lot of heritage hardware that was available to us at the beginning of the program, which was a cost savings. We didn't have to invest in new hardware. So if you're going to fly a lot and your hardware is expensive to build and your stuff's not really available to you, reusability makes a lot of sense from a business standpoint. You don't fly a lot and you already have hardware available to you, then it doesn't make sense to invest in that reusability and take a performance penalty for doing so.
John or Doug, anything you all want to add?
Hey, you know, Mary, I'd like to jump in on this just a little bit because you've got 3 guys here that have done reusable rockets. You know, we did that, and we've done expendable rockets. Really, Mark said it really well. There's a lot of reasons to go one way or the other, but what you've got to do is let the mission dictate. You know, you fall in love with the mission requirements. Like, are you going to go to the moon? Are you going to go to Mars? And then out of that comes all the requirements that the hardware needs. And in this case, when you're going to do an exploration mission that's so vast, you don't do it very frequently. And so the business calculus that Mark talks about is, can I afford this infrastructure to recover, right? Can I afford the ships? And we did that. In Shuttle, we recovered the boosters, and notably, we recovered the orbiter, which is something most people don't do, right? They recover capsules, but we recovered really what is an integral part of that ship. It had the 3 engines on it. And so really there's been nothing, even the things we're doing today aren't as recoverable at all like we had with the Space Transportation System, the Shuttle program. And so we've done that. The 3 of us were involved in some of that, and we know the goodness of recovery. We like seeing the hardware come back. But when you get to that performance penalty, and then also even launch availability, you know, I need to make sure that our orbital mechanics are right for launching, and you have to start weighing in things like, is the sea state okay to launch out on the ocean or to recover on the ocean? All of these come into play with that calculus that Mark eloquently talked about there. If you're going to bring that rocket back to where you launched it from, it's extremely expensive performance-wise. And so really part of our selection is astronaut safety and mission enhancement. We're going to take all the performance we've got and we're going to send all of that capability with those astronauts rather than recover the hardware, because we're only doing, you know, to do this kind of class of mission, just like they did in Apollo, they're not frequent flights. We kind of compress that in our mind as if Apollo flew every week, but they didn't. They flew over a 3-year period. They flew, a handful of missions to the moon. And so we've got the same flight rate. And so I think we've made a pretty good choice for our rocket. But it is great to see that the effort by not just the agency, but industry partners has really culminated in a lot of good recoverable systems to enable different missions. Our mission just doesn't merit that right now.
I'm hearing we chose this rocket. We intentionally chose the expendable design because we really wanted to maximize what we can carry to the moon and Mars. And, there was some legacy hardware that we had available. So, John, were you intentional in choosing a combination of RS-25 and solid rocket motors? But was there something about that combination that really made you go, yep, that's what we want for SLS?
Hey, I'd like to take credit for that decision, but the former chief engineer made that call. But it's a good call, and let me tell you why it's a good call. There's a lot of good reasons in that combination, and in what Doug called so well a stage and a half. You may be familiar. We had different staging. I think you might talk about staging in a minute. But why we chose all of those things in the hardware is one, we understand them well. That engine that Doug talked about, it's not just a high performer, though it is an extremely high performance engine. It's the one we know best. we've got over 1 million seconds of time evaluating the performance of that engine. We know that engine well. It's what you don't know that you have to go work on. And so that helped eliminate a lot of what we needed to work on. It was an incredibly smart choice to take these 16 engines, that some of which were recovered, as we just talked about, all of which are recovered and have flight history. But that engine itself, that design of that engine, and the efforts that Aerojet Rocketdyne is doing to make that a more affordable, now with a different focus, a single flight focus, that engine is just an outstanding choice. And then to take the solid rocket combination that we talked about, it's not the same solid rocket, by the way. It's a bigger solid rocket. You know, if you were to put the shuttle side by side with Space Launch System, and the astronauts have in their mind when they come to the VAB and they look out and they see the VAB full, because that VAB was built, the Vehicle Assembly Building was built for Saturn, for the Apollo missions. And when they see that bigger solid rocket booster and they see this very large core attached, they look at me and they say, well, now this is what this building was built for, an exploration class rocket. But the basic design in our beginning here is very similar. There's some differences, but it is very similar. And so we were able to start with things we understand very well. There's some heritage parts that really mitigate some risk, which is what we wanted to do. There's some what I call legacy parts. That's where we understand them well. We used them one way in the previous design, say shuttle, and now we're going to use them a little bit different. But anyway, I think that gives you some example of that architecture that the previous chief engineer decided. I will also add that we did take a look at other architectures in that initial study back in 2011. We traded everything. And when you trade it, you can have your pet project, but when you lay it out and you look at both cost, complexity, safety, and architecture, this is what fell out as the absolute best decision. So I'm glad that they chose it, because that's why we're ready to launch.
Thanks, John. So Doug, John was talking about your engines. You've been with those engines for a long time. So I think we've highlighted, you know, the reliability of the engines, the availability, you know, the great performance of them. But there's a lot going on with those engines. They're remarkable machines. So do you want to explain some of the key functions and aspects of the engines?
Yeah, sure. You can kind of break the engine down into the different parts, and we have that flow schematic up there. At first, the nozzle is the thing that everybody sees that comes out the back of in the shuttle days of the back of the orbiter, and now our SLS rocket, the bottom of the rocket. That's really taking that exhaust and accelerating it as efficiently as possible and generating the thrust. We already talked about the main injector and the main combustion chamber. If you look at that chart, you can see those kind of 4 components around the periphery. Those are the turbo pumps. They have turbines on one side and then pumps on the other. That's what drives all the fluid eventually into the main combustion chamber. As you can imagine, there are valves. The valves control everything. The valves, just like on your car controlling your speed, the valves will control thrust and how we're using the propellant, sort of like a fuel injector would control it on a car. Then we have the brains of the engine, the controller, which looks at the engine 50 times a second and assesses its health and gives it command. So there are a lot of really great, challenging things to work on. As John was talking about reliability, you know, that's one of the reasons we picked this engine, was reliability, not just for safety purposes, which is the most important, but also for being ready to fly when you need to fly. We're going on the Mars eventually. You lose the launch window for Mars and you wait 2 years for another launch window to come around. So you want high reliability, even getting ready to fly. And so in the shuttle days, I worked on the shuttle for a long time. It was all about reliability. It was about safety of the astronauts. And also, if they're reliable and they're reusable, you can use them a lot. And all of a sudden, the price of the engine gets a lot cheaper. Well, we're not doing that anymore. For, you know, John and Mark described why it's a better fit to have this vehicle be an expendable vehicle But now for the engines, we have to make them cheaper. And so for all of those components I talked about, we've got improvements in all of those components. You know, it's whether it's better manufacturing techniques or making the processes more efficient. And then what I like, we're using 3D printing a lot, additive manufacturing. That's the one that's really exciting to me, which can change our cycle times from days and weeks, or what used to be months and years into days and weeks. So it's a challenging rocket. It's fun to work on. It's complicated, but it's a good choice for this vehicle. It really fit because of the reliability. And like John said, we had 16 in Mark II, we had 16 engines. So that makes it easier for the rocket maker to use up those engines. We're not going to be on critical path. We're not going to have significant technical issues as you're trying to develop that entire rocket.
So, John, you know, Doug mentioned the controller. We have a room full of reporters. We were remiss if we didn't ask you about the controller issue that was, you know, reported on in the December timeframe. So can you talk a little bit about what happened and why that controller needed to be replaced? And even, you know, Doug hinted a little bit about what a controller does, and maybe talk a little bit more about the function of a controller.
Yeah, you know, first let me talk about the function of a controller or any flight software in these modern machines. And as Doug said, these are complicated machines, but they're trying to provide the most simple solution to an extremely complex mission. And that's really what we're doing. The software and these hardware avionics boxes, these controllers, not just in the engines, but in other places, you know, I'd just like to quote my good friend, our avionics lead, when he says, the software is the functional integrator for the rocket. The software tells the rocket what to do. So we need the controllers. We need the software on the controllers. These engine controllers, they're redundant. They've got two channels that both do the same thing. We want that redundancy. It speaks to the reliability that Doug just mentioned. We've used this controller a lot. We've, as you guys have seen, if you're in the press and you've been following space, you saw this wonderful test less than a year ago. We did a full burn with core stage. And then we shipped it to Kennedy Space Center. And we're doing some really detailed checkout testing. That's what if you want to call it, the delay is, or at least people think of it as delay, but it's a planned delay. It's called integrated test and checkout for the first flight. And when we were going through some of those tests, we did have a communication issue on one of the redundant channels for one of the engines. And so we did jump all over that. I'm really proud of Doug's team. It's probably good that you asked me to do this so I can be proud of Doug here. But they should be proud. And in just a couple of days after diagnosing the issue, they were able to fully replace with a new controller. We actually know what's going on there. I don't want to be the press release person of exactly why I have confidence in flight. But as the chief engineer for the rocket, I will be asked, in fact, next week at one of our flight readiness reviews, when I have confidence in that hardware, and I'll be able to tell them because the technical work has been done that we've if you will, recovered, and we have good rationale for not just the controller that we replaced, but all the controllers on the rocket. I think we've got a very robust system. You know, it was out of caution that you take that redundancy and say, oh, I'm having trouble communicating right with this one, and I'm going to go fix it. But that's what we do, and that's why we need to do that. We want that 100% redundancy when we roll out. Part of that is just what Doug said. You know, I can't emphasize enough when you talk about an exploration mission over a low Earth orbit mission, your windows are different. Your windows may occur monthly, and they occur for a day. Or if you're going to, say, the Jovian system, you may have 1 month out of a year that you can go. And if you miss that year, the whole mission changes, and it takes a totally different amount of time. That's the same with the Mars system. That's why Doug was pointing that out. And so for us, when we roll out there to the pad and we want to launch, certainly we've got some days. We're going to the moon. It's similar to what we did before, but you know, you can easily lose more than just a low Earth orbit mission, right? You're not just trying to hit an inclined orbit relative to the equator that's going to happen every 90 minutes. You're looking at you're looking at something different than that. So we want that to work. So in an abundance of caution, we're always going to replace that hardware and make sure it's ready to go. So good job, Doug and the Aerojet Rocketdyne team. You replaced it in 2 days, and we got a fully functional rocket.
Yeah, thanks,
John.
John. KSC guys did a fantastic job at that.
All right. So, Mark, I understand when we like those solids, we're going somewhere. So can you talk to us a little bit about the start sequence, what reporters should expect, and how this rocket's going to get off the pad?
Yeah, so probably roughly about 5 seconds before we light the boosters, the liquid engines power up as they go through their startup sequence, and then a electrical command is issued from the ground, travels through the back end of the booster, and tells some ignition devices on the booster that it's time to ignite, and an ignition signal is sent to the ignition train on the booster. And in about 1 second, we were up to full thrust. And when they go off, as John so clearly pointed out, gravity's not our friend. The boosters are both putting out about 3.6 million pounds of thrust each, and their job is to get us out of the dense atmosphere and away from the gravity well of Earth as fast as possible. So that takes about 2 minutes. And at the end of 2 minutes, the boosters are staged and they fall back to Earth. And the core stage takes over and propels the vehicle on the remainder of the mission.
So, Doug, I failed to mention some of the other engines that are on that core stage. One's the upper stage. And do you want to talk a little bit about the entire flight profile after the two solids separate, or John, would you rather do that?
Either way, John, you've got the whole rocket. Why don't you talk about that?
Well, I've got extremely good partners on a lot of pieces of this rocket, and Doug's one of those. I'll set it up for Doug to talk about the in-space propulsion part. But hey, Mark's got this beautiful, wonderful part of the mission, this kind of lift off. If you've seen a shuttle, it's going to be similar. The rocket doesn't twang. If you guys are familiar with that, we don't have that offset piece there, but we lift off very quickly and we'll be flying through that dense atmosphere. We'll go through transonic and the max Q that we told you about earlier. And then shortly thereafter, we'll go through max heating and we'll drop the rocket boosters, just like Mark said. Pretty exciting time, really. As a former aerodynamicist, I love all of that stuff. That's the dense atmosphere I used to work on. After that, we just continue to accelerate with that core stage. Those RS-25s really take over and put in all the work that we need to accelerate. We're roughly 4 times the speed of sound when they take over to do their part, and we're going to end up at 26,000 feet per second. That's roughly 26 times the speed of sound in atmosphere when we get to orbit, and we do this very large elliptical orbit that we're going to do, and then we separate. And then I'm gonna hand it over to Doug, because it's Doug's engine that does the work on this next in-space phase. And so I'm going to hand it over to Doug. We separate what we've got, we pull that RL-10 out, and Doug's RL-10 takes over and pushes us toward the moon. So go ahead, Doug.
Sure. Yeah, like John was saying, the RS-25s will be done. The solids, they're the sprinters, and so they drop off first. The RS-25 is kind of the milers. Then when they're done, then we can drop off that stage, so we don't have to carry that mass. And then it's up on the second stage for the RL-10s to take over. That's that expander cycle engine that I talked about. And so their job is first to get us in a good circular orbit, while folks on the ground and computers are figuring out, okay, can we commit to going to the moon? Translunar injection, TLI. And so if we can, then those RL-10s will start again. And this time they'll run for about 20 minutes, I think. And they get us going to the moon. Then that drops off. You don't want to carry that stage weight. And what you're left with is the service module, which is on the bottom of the capsule. It looks like a big cylinder or disc, and it's got a lot of in-space engines on it, and then the capsule on top. And so now that's what you're left with. You've got the capsule, you've got the service module, you've got some solar cells out there for energy. And now that main engine on that service module is going to take over, And it's going to do all the in-space maneuvers around the moon in the different orbits. Once the mission is completed, then that same engine is going to head us towards home. And by the way, besides the main engine, we have auxiliary engines that will also help with the space maneuvers. And they're really redundant. If we lose that main engine, we can finish the mission with the auxiliary engines, 8 of them on the service module. Then we head for home. Once their job is done, the service module then drops off. It's just the capsule. And then there are those smaller engines that we talked about in the onset of this discussion, which are for reaction control. They just basically keep the capsule headed in the right direction. Heat shield first as it can enter the atmosphere, and then come in safely and parachutes deploy, and we've had a successful mission. So there's a lot of engines.
Successful touchdown, Doug.
Yeah, a lot of little rocket engines that are involved in this mission. That not just the big loud ones that Mark and I deal with, but a lot of engines throughout the mission.
Yeah, NASA put out a great news feature on the engines and motors. I think there's 55 total across the entire stack. That's a news feature that was put out yesterday. We'll share that with reporters in our follow-up email. But yeah, we're looking forward to that nice splashdown in San Diego. All right, so one last question, and then we're going to go to reporters' questions, and we're going to ask that you put them in the chat since we've definitely had some mute issues earlier. But last question is, we hear a lot about assured access to space when talking about rockets. And so, Mark, my question to you is, what does that mean?
Well, assured access to space means that you always have availability to support the nation's interest in space, whether that be civil space or military space. And this vehicle on the civil space side really is truly a national asset. We're talking about the world's largest rocket in terms of payload capability. That's
All right, I lost Mark.
to DLI. So it's a tremendous deep space capability, and it's built.
I'm losing Mark. Are you all losing Mark? Yeah, okay. All right. So, Mark, we're going to have to come back to you. Your connection's not very good. So, all right. So why don't we move on to the questions, and we'll come back to Mark if we can get his sound a little bit better. And I guess, Doug, did you want to add anything? Because I could not understand what Mark was saying there.
No, you know what? That's too bad. He's got so much experience in this area. But yeah, the assured access to space goes back to reliability from a rocket engine guy. You've got a reliable engine that's going to make sure that you can get there, not only for this mission, maybe for other missions. And that's where Mark's really the expert on expanding that assured access to space, whether it's deep space missions or defense or moon missions or Mars missions. That's really important, I think, for the country.
All right. Well,
Yeah,
let's
hopefully
move
you
over.
can hear me now. But
Sorry, Mark, still can't hear you. All right, we're going to move over to the questions from our reporters. Sorry, maybe I could hear you now.
Okay, so carry on. Doug covered it well.
All right, so we're going to start with a non-Mark question while we work through this technology. Doug, we got a question. Are there any engine supplier obsolescence issues?
Yeah, that's a great question. In fact, we call this first stage of our program the adaptation part of the program, where we adapt the old, if I didn't mention it, maybe it's obvious, these are RS-25s are adapted from the SSMEs. Oh, John did mention that. We did have supplier obsolescence problems. Some suppliers were out of business that originally built the hardware. So part of the adaptation was making sure we could support these 16 engines. And then beyond that, we've got the part of the program that's called Restart. What about those suppliers that are gone? We need to find new suppliers. Even in our own factory with the things that we make, when you go 15 years without making a very complicated part, you've got some relearning to do. So whether it was obsolescence or suppliers are out of business or just relearning what you have to do. Yeah, that was a big part of the program. We're in the midst of that right now and learning every day. I think all the elements had to do something like that as well.
All right. So, John, I think this is probably a question for you. If you were going to design the SLS from scratch, what changes, if any, would you make?
Well, while I like the question, and it would be great to just have this unlimited canvas to create an homage to ourselves, the reality is that you're constrained by time and resources, and there's other objectives, like how do you fit within the aerospace industrial base and things like that. And so, quite honestly, we are changing the SLS. Let me just say that the changes that are coming in terms of the Block 1B and Block 2 are the changes that I would make. I would make it, bigger payload. And in fact, we've got an evolution roadmap that goes into the 30s. So first of all, let me say that, from a physics basis, we have a very capable machine based on experience. And you're going to optimize around something. And we optimized around essentially that, mission safety and leveraging knowledge and really getting this thing fielded. Would you build a big monolithic hydrocarbon if you had an infinite amount of time? Like if time wasn't a metric, you would choose to do that, like they did in Apollo. But honestly, it doesn't play as well as these engines we do understand. So let me just say that while I really like the question, what I really think is the changes that we have coming in the Block 1B and the Block 2 are the changes that this system, and we planned it from the beginning, that will make this rocket even more and more capable, right? We've got a great evolution roadmap to make this rocket just more and more capable from the beginning.
All right, well, we got somebody that recognizes this is a test flight. This is the first integrated test flight of SLS and Orion, and so they want to talk about abort capability. And they want to know what are the options for one engine out case. So if one of your engines fails on the way to orbit, can you still get to orbit? And also RS-25 thrust settings at T-0, max Q, and late in the flight for G limiting. So Doug and John, I'm not sure which one of you wants that one.
Doug, do you want me to talk to it, or do you want to talk to some of that?
Either way, John.
Hey, I'll just mention we do have a lot of boardability. I don't know what is releasable in terms of our analysis on exactly, but let's just say that even if we had an intelligent engine problem right off the pad, we will have a mission that doesn't just end in an early disposal or a range safety detonation. So I'll just cover that part and say that. And then I'll just mention that, whoever this questioner is certainly knows a little bit about rockets. Traditionally, we did throttle down. We do throttle down during very select pieces of the mission. I think last week I had an interview with somebody, and I'm able to at least say what we said there because I know that got released, and that is that most of the months we actually do not throttle down during the transonic or max Q in this rocket. We're carrying a lot of rocket. We're pushing a lot of rocket. There are times where we do have enough energy to do that, and so in those cases we do have some condition limiting parts that will just throttle down a little bit. But then, as Doug will talk, and I'm going to hand the ball to him, at the end of flight, you got these beautiful engines and you've lost a lot of mass and propellant because he's been sucking those propellant out like swimming pools every 20 seconds, just like he said. So, Doug, you can talk to us about that final phase of flight.
Yeah, and as far as the aborts, just depends on where you are in the flight, and so it's not an easy answer. In the shuttle days, you probably remember for max Q that John described, we would have we'd go into a bucket. We would throttle down to about 65% power level. We don't have to do that on this rocket. But there are different missions and different profiles. And so what will happen is the mission architects will give us the profile that we need to run. They'll determine that for us. The engines themselves, of course, they're throttleable. And so whatever that mission happens to be, we'll be able to throttle those engines accordingly. And then just as a tidbit of information, towards the end, we'll throttle them down like we used to. You might remember in the shuttle days, we had that slow throttle down to keep us going at about 3 Gs, and we're going to have something similar to that.
Whitney, we had a request to show the last slide that you had up, so I'm hoping you know which one that is. Mark, I'm going to test your sound to see if we can hear you.
Can you hear me?
Can hear you. All right. It might be easier to turn your video off. That might be pulling some. So if you want to turn your video off, that might help with the quality. But so I think you were the one who was telling us a little bit about reusability and expendable. And so they would like to know, how many missions would you need to fly to the moon to change the calculus and make it more economical to fly reusable rockets rather than disposable?
There's been a lot of studies done on that, and like I said, it depends a lot on the cost model that your business is running. But typically, if you get into the mid-teens, into the 14, 15, 17 range of launches, that is a really, really good sweet spot for reusability. I have seen studies that are as low as 9, 10, depending on the cost models. But you need to get into that range where it really starts to make sense.
All right, and I see, I'm scrolling through all the questions that I wasn't on complete order, but I think some of that, there are also the question here about, there is another rocket out there, the Starship, that's got more payload capacity. Does that change the reusable, disposable calculus? So any comment on that? I think their design is a completely different architecture, and we are going to have a series on mission architectures later. But do you want to talk about sort of how that architecture is different than this architecture?
Yeah, if you're talking about some of the commercial architecture, deep space commercial architectures like Starship or others, they rely on a completely different system architecture approach. They're utilizing fuel depots in low Earth orbit. These approaches require multiple launches, many launches, in order to pre-position fuel assets, of which you then reach low Earth orbit, refuel there, and then go on your destination to cislunar space. That is not what SLS does. SLS has very, very heavy payload capability in a single launch. It does not rely on the need to stop over at the gas station on the way to the destination. And so in order to compare their performance numbers, you have to first do some apples and apples ground rules as to how you would do that. But they're very different architectures.
All right. And then you, Doug or John, want to add?
I'll just add that they are an Artemis partner, and we plan on using the capabilities that exist in industry. They're not for the human transport per se, but for other things. They intend to have a large flight rate for other reasons, for commercial reasons, not for the exploration reasons. That's what drives them to part of their architecture. And then, so it's not designed really for the safety and optimization that we do for exploration, but it appears that we can use that rocket. And so they are a partner of ours in the overall Artemis mission space, and looking forward to seeing how that develops.
All right, we got a lot of questions here, so we may have to get back to folks in written form, but I like this question. Which part of the Artemis 1 trajectory will have you holding your breath the most? Launch, TLI, something else? So I'm going to ask each of you that question. So Doug, I'm going to start with you.
Well, our engines run for about 8.5 minutes, and it turns out you can hold your breath for 8.5 minutes. the most, I don't know, I wouldn't call it concerning, but you're really watching carefully the whole launch, but it's the first 6 seconds. You know, Mark talked about that. We have a hold down for 6 seconds. Our engines are running. The controllers are making sure they're okay, because once you launch Mark's big rockets, you're going somewhere. So we are fixed on that data at first. We're an unattached steering wheel. We can't react quickly enough to do anything about it. But I'll tell you what I'm personally doing when I'm in the launch room, I'm looking for the mock diamonds. The mock diamonds are those triangles under our engines. When I see those 4 mock diamonds going, I know we're up to speed. It looks like everything's okay. And so that's what I really look for on launch day. That's exciting.
All right, John, I saw a smile on your face. Where are you going to be holding your breath?
Well, I'm going to first say, you know, I have a unique role on launch day. I've got these great teams, and I get to represent them in the firing room. And so I'll be in the firing room, and I'll be helping integrate. And so when Doug sees something, it won't be as late as the mock diamonds, because if we don't get the right mock diamonds, we're shutting down and we're not launching that day. But hours ahead of time, this team, Doug is going to be on station, and Mark's going to be on station, and there's teams with them. And when we have issues, those issues come through us. And we've all been training for this. Actually, I've talked to them on simulated launch days. And so for me, I'm going to be really busy. I was a little bit laughing because every element is going to be worried about their hardware. And I've got to be accountable for all of those particular events that occur all the way through TLI, all the way through the long burn of that RL10. But let me just say, it really comes down to the preparation and planning. And so for me, it is liftoff. After liftoff, the machine is moving. We have wonderfully thought out flight rules. You know, that question about the aborts, we've thought about that. We've got pre-programmed contingencies that occur during the flight, should an engine shut off or other things. And so at that point, once we lift off, we have placed the rocket in the hands of our pre-thought, of our planning, and flight rules dominate. And our good friends at Houston, flight controllers, will be monitoring that, and we'll be along for the ride with them. But once we lift off, our decision making is complete for that day, and the decisions that we've made previously will feed into the flight of that rocket. So launch, that's what I'm worried about.
Yeah, so I'll give you the hardcore steely-eyed rocket man answer, which is, if you've been in this business long enough, you quickly realize that space is a challenging business. And there are pitfalls all along the way. And you start to think like a systems engineer, and you start to worry about the entire system. So yeah, parochially, I'll be excited. Hey, the booster staged off after 2 minutes. We delivered our contribution to the vehicle. But I'm interested in the mission, the overall system. And we aren't successful until we've reached our destination and folks are safely on orbit. And so I'm not interested in any one thing. I'm interested in all of it.
All right. So we got another question here. So following up on the expendable question. So let's see. You said that you're not planning to fly a lot, but shouldn't that be the imperative for NASA and the United States to some degree, to fly a lot more than is currently planned, and then support the technology needed for that future?
Yes, so let me take a shot at that, John. Yes, a greater flight rate is in the direction of goodness, and we've talked about the SLS as a national asset, and NASA is currently moving to a new model that would enable that vehicle to perhaps be used as a national asset. And so, yes, I think we're taking steps in that direction to try to garner more interest in flying longer. Lots of realities associated with flying more, budgets, hardware availability, all these things can be overcome. But it is such a national asset. I think everyone could take advantage of it in the future.
All right. we're running low on time, but another question here, will there be additional abort capabilities for crewed SLS flights versus Artemis 1?
Oh, yes. Let me take that one. Certainly for any, crew safety is our number one thing. We don't have a crew on board on this flight, and so there is not an active launch abort system. You will see it there in its outer mode line. You will see that will be actively loaded and ready. One of the key things of Artemis 1 is actually that all those abort triggers that would send that system to pull that capsule off, or if you're late enough in flight and you've removed that system and then you'd fly to a different abort scenario, all of those triggers are active to evaluate this prior to putting our colleagues, our friends, on this flight. So yes, for Artemis 2, we will have an active launch abort system on top of the rocket in order to provide additional crew safety.
All right. I think this could be a whole nother series, but what are you guys doing to decrease the cost per launch of the rocket? Because Doug, I know you're doing lots and lots to decrease the cost, but I feel like we could be here all afternoon if you went through all of that.
Yeah, I mean, just in short, we've taken a modest shot at it. The Marshall folks, our colleagues at Marshall and NASA gave us a challenge to reduce the cost of the engine 30%. It looks like we're doing that for the reasons that I had talked about: additive manufacturing, advanced manufacturing, all those sorts of things. We're looking at all aspects of the program. We even have actually things in motion now that will get us even more savings. We can cut the cost in half. So the short answer is we're always looking at that. We're actively pursuing reducing that. For an expendable vehicle, it's much more important. So we're going aggressively after that.
All right. Since we started 5 minutes late, I'm going to hope the speakers will give me a 5 minutes grace, and I can ask Mark one more question. So, Mark, what is the typical lifetime of a fully fueled solid rocket booster, and how different is the solid fuel being used on SLS from the mixture used on the space shuttle?
Okay, let's take the last one first. The propellant that's in the SLS is very, very similar to what was used in the shuttle. It is the same family of propellant called P-band. The only changes that were made from the shuttle formulation were to tailor the way the propellant burns, how fast it burns. So we tweaked a couple ratios in ingredients in order to do that. But it is, I would say it is a very, very close cousin of the current or the old shuttle propellant. The second question was, how long can you store these solids? We are, by contract, certified to 8 years for the loaded motors, and so they can be stored in over that 8-year period of time and be ready to go for any mission. Solid rocket motors in general have very, very long shelf lives. There have been solid rocket motors that have been in missile silos for well over 40 years that have been test flown and meet their original specifications. So solid propellants are very stable over time.
All right, John, anything you wanted to add there?
No, Mark's got it right. That's it.
All right, well, so we did get a lot of questions. I got some privately to everyone, so hopefully we've captured all of them in a Word document. We'll follow up with folks if we didn't get to your question, because there were a lot of really great questions in there. But hopefully this was a good session for everybody. Hopefully it was informative. I know we covered a lot of different things, but if you need anything, we'd love to hear your feedback, and please reach out to us. And if you have additional questions, we'd love it. But I want to turn it back over to our host, Frank Slazer, and thank him for inviting us to have this Rocket 101 series.
Thank you, Mary, and thank you for the participants. Really appreciate you guys doing this. What I really appreciate is the fact that so many people from the media joined in. I think we had almost 50 people And of course, this is going to be hosted on our website, so you can certainly tie in later if you missed part of it, or if you have a colleague that might potentially be interested in. We are really looking for your feedback on this session. Obviously, we had a little bit of technical difficulties, but we are going to get better at this over time. And this was, I think, more or less, straightforward. But we're also going to show you a short video about the time lapse of the Artemis 1 stacking effort. Maybe you can run that while I finish up my little narration here. Our series is going to continue over the next few months leading up to our launch in April. If you cannot make a session, but you're interested in the content, it'll be archived and available on the Coalition's website. Our next webinar is going to be announced very soon, and we're going to send an announcement to you at your email address. Topics we plan to cover at this point include mission architecture planning. How do we get to the moon? Deep space versus low Earth orbit. Why explore and why explore with humans? Artemis 1 opening the doors to a sustainable presence. We may also add additional content on additional topics related to space exploration, even after the Artemis 1 mission is concluded. Feel free to offer your suggestions or your requests for future episodes. And again, any feedback you provide would be sincerely appreciated. Thank you so much for joining us today. Meanwhile,
Thank you, John, Doug, and Mark. Really appreciate it.
Yeah, very much so.
Appreciate the opportunity.
Yeah, my pleasure.
Yeah, mine too.